The second half, we start with the system identification, and you don't feel very much, familiar with the system identification, but it turns out to be a very important, part of the engineering analysis. Identification and learning are closely related, in fact. So given the series of, the data, time series data, input and output, we'd have to build the model that can actually predict the output in response to input, right? So estimations and prediction that we've been discussing in the part 1 and 2, but that's mostly given some plant model. And based on that, we'd like to predict the output in response to input, right? And now the question is, so how do you build the model? Models, maybe you are given some models, but oftentimes, you have to build the model that represent your plant, right? And in doing so, we use the data-driven approach. So we have some input to output the data, and what you want to do is to create the model that can actually predict the output in response to input. So that's a system identification. So having said that, given some input to output, we like to build a model. This is very similar to learning. Learning and identification are very close. Having a little different emphasis. Identifications, more or less, technique has been developed for the linear systems, and the learning is actually emphasis is actually nonlinear map, nonlinear systems. So it's a little bit different. And then, but both is to build the model to predict the output, either through previous data, that's learning, or some kind of a given or acquired data. That's actually system identification. So today's lecture is 260, lecture 13, non-parametric linear system identification. And this is the global view of the second half of the course materials. So the objective is identification and learning, and underlying principles and all kind of important part and the techniques, basically system representations and the modeling from data, right? And we have part 3 and 4. Part 3 we focus on the linear systems, and part 4 the nonlinear systems. And on the linear systems identifications, system identifications, we have 2 branches. One is going to a prediction error model method versus a subspace method. Subspace method is connected to so-called state space representation, like the equations we use in the Kalman filter, right? X dot equal X plus BU. That is and actually the target that we'd actually apply this method, the subsystem method. And the prediction error method is basically, prediction error formalisms. And we apply this one mostly to transfer functions and impulse response in the time domain. We have a non-parametric representation and a parametric representation. And in the non-parametric representation, we have time domain method and the frequency domain method. So actually system identification itself is kind of broad, combined with the linear and nonlinear systems. But I know we just picked the one good set of materials to be covered in here in the part 3. Part 4, we go to nonlinear systems. This is yet another big areas, and then very much overlapping with the machine learning and the nonlinear system modeling. We started with the just a fun, standard one, like a functional approximation, the neural nets, radial basis functions, and and the multi-layer neural nets, error backprop, and CNN. If time permits, we look at the recurrent network. We spent some time on kernels, which is very important concept. We started with the support vector machines, and that's the standard materials in the machine learning. And we go to Gaussian processes. It turns out a very useful, important concept. At the end, we look at the new materials, the lifted linearization. This is only 7 or 8 years old, but these days it's really actually bubbling up, and then very much important technique. So here we separate the linear systems to nonlinear systems, but there's a technique to linearize nonlinear systems, representing it in a linear form. However, it is not just a simple approximation, but it's exact. And the Koopman theory tells us, a broad class of nonlinear systems can be represented in actually linear form, linear equations in infinite space. And we need to cut it down to some finite representations, and then approximation comes in, but still it is to provide a very accurate representation of nonlinear systems in linear domains. And the techniques are being applied to model predictive controls, and actually it's hard to solve the nonlinear MPC problem, but it is converted to a linear form, so computationally it's very quick, and having no chance to get stuck at the local minima. You get the you just solve the convex optimization problem in a very quick manner. So all these are materials in the second half. Now, every year I observe the students having a little bit of difficulty to study the second half of 2160 for 3 reasons. One is that we look at the kind of a concept which you have never heard of, right? Common filters, everyone knows, and everyone have heard to some extent. But in the second half, you'll be exposed to more unfamiliar materials. That's number one. And number two, somehow this part 3 in particular, you need to record and review the kind of basic systems and control materials. So some prerequisite makes a little bit of difference. You need to know, you need to review something which I indicate specifically if you're not familiar with those materials. And the third reason is that the little bit in the high pitch, we cover a lot of materials. I hope you want to get the burnout. It's a little bit of a challenge, for the second half. But I guarantee you that this is not a complete, topics, but it covered very well the data-driven method applied to system dynamics and controls and machine learning problem. There are many actually, the techniques are quite useful in the practical programs. So today we focus on part 3, going up a prediction error method and the non-parametric the branch. And then we look at both the time domain and the frequency domain and the system identification method. So first the question you may ask, what is the non-parametric representation? So to explain the non-parametric, I have to explain the parametric representation. Parametric representation of linear systems, a time invariant. They may be in a transfer function like this. So here you have, undamped natural frequency omega n and damping coefficient in zeta. Also, B1 and B2 are another set of parameters involved in this transfer function representation. So this is one parametric representation, right? Like a state equation 2, x dot equal ax plus bu, y equals cx. This particular structure associated with the and parameter as ABC is basically a particular parametric representation. So non-parametric representation doesn't depend on any of the specific model structure. Instead, for instance, frequency domain, body plot. It's just a plot. But I know this is a representation of the linear time invariant systems. But likewise, in time domain, impulse response is basically the way to represent this. So, by discretizing this, for instance, the series of this time response weight represent the systems, which is very much, on the general. It doesn't depend on a particular representation, system order, system model like this. So let's look at these, stuff today. So first, the way I like to do just a quick review of impulse response. So here's the linear time invariant systems that we deal with throughout this part 3, linear time invariant systems. Input to UT and output to YT. And then let's think about the special input, which is called the impulse input. And then that's actually one hit, and the area here is 1, and then actually time duration is infinitely short. And then when you hit it, the system is the response to that kind of hiccup, move up and then down usually. So this is the impulse response. Now this impulse response is very fundamentally important because even though this guy is for this particular form of input, but with use of this impulse response curve, we can generate output for any curve input like this, okay? Because this input to UT can be segmented into many small short-term slices, and each of them is the type of impulse with the magnitude, amplitude dictated by UT. And then let's see the response to the series of such impulses at the time t equal t. So if you look at the one impulse, tau second before, you hit this guy, and then the tau second later, you get the this response as a contribution from this input, right? So what you need to do is actually take out the impulse response tau second later. So G of tau, and then times input impulse at here is actually a magnitude of ut minus tau. So we multiply this, and then the impulse, and there are many of them, right? So we apply the superposition because this is a linear system, so we can use a superposition principle, and then we take the summations or integrations over the whole time span. And then that's actually convolutions, right? You remember this convolution. Okay, we use this convolutions and then impulse response. So now we look at the discrete time. So instead of a continuous time, we discretize it. So impulse response is gk, k equals 0, 1, 2, 3, like this, right? So now for the sake of brevity, we quietly assume delta t to be 1 because the real t is actually sampling interval delta t times k, but we just assume that the delta t equal 1 and use the t and the k in an interchangeable manner, right? So impulse response in discrete time, we can write it then yt equals gk, ut minus k, k equal 0 to infinity. Then that's actually the impulse response. Now here we use a special the terminology notation in system identification and then other fields. It's called the time shift operator. We use a Q for this. So this Q advances the time index 1 unit time ahead. So if you put the Q here, Q times UT, this means UT plus 1. Q square UT is actually Q times UT. Q UT is actually UT plus 1, and then apply one more Q here. That becomes UT plus 2. Q minus 1 is a UT minus 1. Okay, so if we use this kind of time shift operator, then this impulse response convolution can be written in this way. So, UT minus K, let's look at UT minus K using this time shift operator. This can be written as Q minus K UT, right? Q minus K UT. Now, putting this together, factoring out the UT, putting this together, summation K 0 to infinite, this guy, let's replace this one, function of Q, GQ. And it turns out that this one can be written as GQ times UT. So convolution becomes the product of this function and the UT. So the impulse response is represented as a polynomial of time shift operator Q that's actually a polynomial function, so GQ. And we call this a GQ, the transfer operator or transfer functions. Obviously, this one is strongly connected to your familiar transfer functions in conjunction with the Z transform. And I'll explain the relationship to Z transform. But for the time being, this is a transfer function or transfer operator. So it's basically an operator in this stage. Okay. Now, the impulse response test. So what you need to do is just you hit the systems by putting this impulse, and then you measure the output, right? Yeah. So discretizing this in this way would like to obtain these and the values, right? However, the challenge is that any kind of measurement like this measurement is corrupted with some noise. Let's say the VT. So let's add this VT for the output here. This is something coming through this, and then we add the noise VT to this expression, right? Let's now actually, we applied impulse. So impulse is something like this. At t equal k, this is non-zero, otherwise 0, right? So substituting this one into this, yt equal a times gt plus dt. So to obtain the gt, it can be estimated as, yt divided by a, gt plus 1 over a bt. So this kind of naive method, they have the one problem, right? Always comes with this. To eliminate to reduce the effect of this noise, what you need to do is just use, larger A, which is actually you hit stronger, strongly. But even though you hit, the system with a large impulse, but there's a physical limitation to it. You can't do that, too much. And then some systems are very fragile. You can't actually apply any big signals into that. So what do we need to do? And here's the clever technique. It's called the correlation method. Okay, correlation method. Okay, excuse me. Yeah, this better method, correlation method is basically we can eliminate the effect of noise. So the idea is the following. So we apply a time sequence UT. This guy is designed to be uncorrelated with the noise VT. Oftentimes we use the random signals here, uncorrelated white signals over here. We inject that one into this. And the this and the this are not correlated. Now, what we need to do is to take the correlation between UT input and the observed output YT, which may be corrupted, containing some kind of a noise of VT. However, the thing is that as you take the correlation, UT is designed so that it is not correlated with VT. And Y bar is to be, of course, correlated with the UT because it is driven by this. So this is the output, right? So when you take the correlation between UT and YT, this component of VT, which is not correlated with the input UT, will be filtered out. It will reflect the only Y bar T, that is actually driven by this, thereby correlated with this. So that's actually the principle. Okay. So yeah, what you do is basically, let's represent this true, noiseless output to be denoted by Y bar, and then plus XT and VT, excuse me, right? And we take the input-output cross correlation, which is given by this, right? Remember that this is the product of UT, YT plus tau, and then take the expectation, right? So, let's substitute this one into this, break it into two terms, but in this particular second terms, UT, VT plus tau, we have designed the UT to be uncorrelated with this, so we can, slash out. So we get this guy, okay? So this is the basic, trick. Now, however, the question is, how can we actually, our objective is to obtain this, discrete form of impulse response, GK, right? And how we actually, extract the GK from here after we take the input-output correlation. That's actually, the issue, and that can be solved by Wiener-Hopf equation. Okay, Wiener-Hopf equation. So let's look at this next. So first, Wiener-Hopf equation provides the theoretical foundations for the correlation method. So it's very important. And we consider a time sequence input to UT, right? Which is assumed to be wide sense stationary. What is wide sense stationary? Do you remember that? Wide sense station have to satisfy two conditions. So one is that the mean value is actually constant and along the timeline, over time. And then this correlation must exist. Autocorrelation exists, and it does not depend on time. It actually depends on the difference between two snapshots, T versus T plus tau. Difference is important, but wherever you take this product, T, it doesn't depend on T. So it's actually separated from the T. It's actually in this list, tau alone, right? So this autocorrelation does exist. Now we assume one more very big kind of a mild assumption that the process is ergodic. Remember the ergodicity? So this actually expectation, it's basically if you look at the definition of UT plus tau times probability density, joint probability UT and UT plus tau, joint probability, right? And they take the integral. So that's actually ensemble mean of this guy, exactly definition of this. However, that actually ensemble means equal to the average over time axis. So here UT plus tau is basically observed over minus n to plus n period, okay? And then we take the average of that. And then actually we push the n to infinity. And if you do so, this is to agree with this, ensemble mean. So that's actually ergodicity, right? So we assume these two. And then what we like to do is to obtain this, discrete impulse response applies to, we look at the linear time invariant systems, and we like to extract, this GK from this cross correlation between input and output. Okay, so now this is actually what we have done, and this is the using the ergodicity assumption. This can be written in this way and extends to infinity. So first thing is, let's look at this. This guy is basically output YT is coming from this process. So, it should be written as the, convolutions, right? Convolution. So G tau ut plus tau minus k, because the t plus tau is actually, you treat this one as the new t, and then that's sitting here, a minus k, and sitting here this way, right? So we just shift this one to t, right? So this can be written in this way. So substituting the convolution equation, this, and actually, that's where we are now. We replace this one by this. Here we go, this guy. And the next, we swap these two summations and put this one inside of it. Okay, so, first the summation over k, putting it out, and the GK can be factored out this way. The remaining part looks like this, the remaining part, right? Limit and 1/2n plus 1, the summation ut, and pick this one here, ut plus tau minus k, and then again the GK is factored out. So look at this. What is this? This guy is the same input, the ut and the ut plus tau minus k. So this one is basically autocorrelation of the input. So RU, and then now carefully look at this. The tau minus k is the index, right? And that's the difference between this and this is tau minus k. So that's why I have RU. That's our autocorrelation, and index time difference between two slices. It's tau minus k. Okay, and then multiply the k, and then take a summation. So that's sitting here, k equals 0 to infinity. Oh. So now we can successfully extract this impulse response GK from the expression of the input-output cross correlations, right? So this, this is the result. This is actually called the Wiener-Hopf equation. If you just compare this one with the convolution, right? So this is the input, this is the output, and then actually impulse response is sitting here. Take the convolutions here, right? Well, look at this, is so similar. Instead of input to U, we have input, autocorrelation, and then instead of output to Y, we have input to output cross correlation. Okay, but this expression is so useful, because we can actually solve the impulse response problem. And then again, we can get rid of the noise. That's actually the main part, right? Now, in using this, maybe we should assume that the impulse response usually infinite long, but we basically cut it out, truncate at a certain point. If the system is actually stable, GT goes to 0 at the end of the day. So, we can set to some threshold, we can truncate it, right? So, this is the capital N, it's not the infinite, and we truncate it. Likewise, the Wiener-Hopf equation 2 can be truncated. Well, in the previous equation, you set the G, K, K is, more than N, it's just a 0, and then you get this expression, right? The same thing. So, let's write this one, write out this. So if tau equals 0, okay, so this is the, RUI 0, okay? So first element k equals 0, and then tau equals 0, you get the RU 0, G 0. And then let's say k equal 1, G1, and then tau equals 0, so minus 1, RU minus 1, G1. and you can extend it to RU minus N GN. If you put the RUY1, let's say tau equal 1, the first one, the K equals 0, it's RU1, and you can just extend it that way, right? So this is the just the expanding expression. This can be represented in vector matrix form. So here we are. RU0 is actually, I put in the G0 to Gn in this way. RUY0 is basically this row times this actually column, right? That is to give this guy. The second one is, as I said, RU1 times G0 and RU0 again, the G1, and then this way. So shifted to this way. So we can make an n by n matrix Rn in this way. So if this Rn is non-singular, we can obtain our G0 to Gn from this cross correlation. So that's where we are. G0, G1, Gn equal Rn inverse. This is n by n matrix inverse. And then actually sitting here are basically input to output cross correlation from time 0 to n. Okay, now consider a particular random signal to be used for the input. And that is actually uncorrelated signals. So if that's the case, RUT UT plus tau is basically non-zero only when tau equal 0, right? Others actually uncorrelated. So if the tau is some value, then rather than 0, it's all 0. So if this is the case, let's obtain Rn. Rn, remember this guy, this is the expression. And the tau here, other than the 0, it's all 0. So we put all 0 here. It turns out to be, and then in the diagonal terms over here is all lambda. So we get to this diagonal matrix, right? So if you apply this to the systems, then Rn inverse is minus 1 over lambda for the diagonal terms. So each of them can be written in this way. Okay, so again, the main point is that we can get rid of the noise coming to the system. So note that the input sequence is generated such that it does not correlate with the noise. Therefore, it is eliminated, as shown, demonstrated previously. This is the correlation method and for identifying the impulse response quotients. Okay, so that's where we are. And let me just take the no questions so far today. Okay, so what time is it? Okay, we are good pace. So let me just show you just one example. So let's see. Let me just use this tool again. So I know, that the we have a systems, right? So linear time invariant systems, right? And we put the UT, which is actually kind of the random signals, very poor random signals, and then we observe Y. Even though some noise comes in, but we take the correlation between the two, RUY, okay, and this is great. It's actually independent of noise. That's great. Now, if we use a U to be very much, truly uncorrelated the signals, which is actually, if you plot the, let's see, plot the RU, U tau, it's a tau here, right? That the, ideal uncorrelated the signals, if we use that for the input to U, it is represented just a 1 point here, right? 1 point here. That's actually we use a lambda. And then others are all 0, 0, 0, right? 0, 0, 0. So, tau equal 1, that's actually, remember, U, for instance, the tau equal expectation, right? U t and ut plus tau, right? If tau is actually other than the 0, it's all 0, right? This turns out a very simple expression that g of the t equal, input the lambda, and then output r u y, the t, right? So this is a simple one. Now, in reality, input signals cannot be that actually random. So it has some correlation. Let's see, r u and then the tau. Of course, at the 0, you have a very strong value, the lambda, right? But tau equal 1, or symmetric here, -1, it's not exactly 0, having some components here, some components here. Okay, let's see, this guy is 1, this is a 0.2 and a 0.2. How can we actually modify this? It can't be this simple, right? So how do you do that? Then we go back to Wiener-Hopf equation, right? So remember that Rn, this is actually concatenations of all R component, right? So input RU0, RU1, RU2. Well, no, this line is minus, but minus plus are basically the same. So, you don't worry about that. 1, RU0, right? Okay, so you have to use this. And then putting this one here, it's going to be, 1, 1, 1. Maybe we can truncate this at some particular point. And here, it's not the 0, but the 0.2, 0.2, 0.2, 0.2. It's going to this way. All the others are all 0. All other 0. So you have to solve this equation, right? And G0, Gt, if you want to truncate it, up to capital N, equal, you have to take the inverse to this Rn inverse, and then RUI 0, RUIN. You observe this guy, as a correlation between the two, these two, RUI is to be plugged in here. So this is the process you need. Is that clear? So that's the things that we can do. But anyway, this all comes from Wiener-Hopf equation. So Wiener is a great person, former MIT professor here. He did so many great things. Okay.
Professor.
Oh yeah. Okay, go ahead.
So, is there ever a case where Rn is singular?
Oh yeah, great. Yeah. Right. Good questions. Yeah. So obviously, if diagonal terms R0, okay, is non-zero, that's actually a very strong case. So even though that's actually not the case, there may be some other situations that may happen. But if input is somewhat, somehow having some particular relationship with the impulse response GK, GK may, having some 0 point, 0 is to cancel with the input, the signals. That's actually a little bit a tricky case, but that may occur. But as far as the input signal is truly uncorrelated, that does not happen. So this technique is very much, we exploit random signals for identifying systems. So perhaps you have learned in the undergraduate control courses or their laboratory, you use some step response or actually sine waves. Look at that, those techniques, right? But once you learn the system identification, we use mostly random signals. So shaking the system, that kind of stuff is much more, effective, much more, informative, and then killing the noise in a clever way. So that's the techniques being used. Okay, thank you for the questions. Oh, two more questions. Charles, how realistic is it to assume you can?
Yeah, it's out of date.
Yeah, that's right. Yeah, this is a really great question. So, yeah, oftentimes that's not actually possible. So we have to limit the bandwidth, and that's actually exactly the topic related to stuff in the next part. So let's move on to frequency domain approach to non-parametric system identification. So what we'd like to do is basically now moving from time domain, to frequency domain. And we look at how we get the body plot and the Nyquist plot. These are basically just two very famous plots, frequency response plots. So frequency response, the frequency domain approach has been widely used in industry. Industry really loves this. It is practical and quite robust, having many effective tools already available. But studying this from the system identification viewpoint, you need to, and we need to introduce, or to someone it's just a review, of discrete time Fourier transform, and the power spectrum, and the cross spectrum, and the frequency transfer function, and finally coherence. These are the kind of mathematical tools that we use, in frequency domain system identification. So let's start with the discrete time Fourier transform. I think everyone knows the Fourier transform, but this is the discrete version. So we deal with the discrete time sequence, xt minus 1, maybe this one going forever, both directions. Okay, and then, we introduce this delta t and sampling interval delta t. So discrete time Fourier transform, the definition is basically given this time sequence xt, we multiply exponential minus I omega k, and then the k, taking a summation from minus infinity to plus infinity. So this is the definitions of discrete time Fourier transform. Here, exponential minus I omega k is given by, this one is basically complex number. It consists of real part, which is cosine omega k, and the imaginary part is I times sine omega k. Okay, so you can think about the unit circles, and then this is two components, xy components, real and then imaginary. So this Fourier transform is actually a complex function, of omega. And from this definition, it is obvious that x omega is a periodic function. If you replace omega by omega plus 2 pi is going here, so it is basically a periodic, and so it is actually the same expression as before. So we basically vary omega from minus pi to plus pi. And then you feel that kind of strange. No. We deal with the high frequency and stuff, so why not confine the minus pi to pi? Well, the one caveat is that for brevity we have set the delta t to 1, right? Sampling interval to be 1. Okay, but now we obtain the real physical frequency, so we must convert the frequency omega, using the DFT to real physical frequency. Okay, so this omega is a very special one, and we need to push back to real physical frequency. So this is our discrete time scale definition, right? Real physical time t is delta t times k. right? Let's multiply omega real, the real frequency to both sides. Then what you get is omega real delta t times k. So this is a non-dimensional quantity. And actually, this remains the same for whatever the kind of scale, time scale you use. So in this particular case, we use a time scale using the sampling interval delta t, and then actually it's getting the time index is basically k. So this particular part should be the omega when we use this time scale k, right? Time time index k. So corresponding to this one is omega. So omega and actually real omega is related in this way. So omega real equal omega over delta t. So just to take one example, if delta t is 1 millisecond, then omega real is basically omega times 10 to the third, right? Because actually delta t is divided here, so denominator. So we have to multiply 1,000, here. So even though it say the range is minus pi to pi, but real omega is to spin minus 3,140 pi radian to plus 3,140 radian. That's actually the real physical stuff. But yeah, we somehow normalize it by the delta t equal 1. We put everything into between the plus minus pi. So that is the one that we like to use for discrete time Fourier transform. Now, inverse transform, you know that the Fourier transform, we don't lose any information, so we can recover the original one from the Fourier transforms, discrete Fourier transforms. And now we multiply, yeah, we multiply not the exponential minus I omega k, but a plus I omega k, right? And replacing this one by this expression, we get to this expression. Yeah, I just changed the notations index from k to L because k will be used, it's being used here. So we just changed to L. So combining these two exponentials, we get the exponential I omega k minus L, right? So I know what you do here is XL and the rest of part, we just swap the summation and the integral. Looking at this integral, this actually, exponential is basically containing cosine, the sign, right? So if you integrate it from minus pi to pi, one full period, and most of the cosine sign becomes 0, right? Integrate is 0, except for the case when the exponential, this part is 0. That's actually L equal k alone. This one survives, becomes 1, and then integrated the minus pi to pi. So the answer is 2 pi. So 2 pi times xk, because only at the k equal L, this is actually non-zero. So we pick only the case L takes the value of k, so that's the xk comes in to 2 pi. So solving this one for xk equal 1 over 2 pi of this expression. This is the inverse discrete time Fourier transform. It completely recovers the original signals. Okay, now power spectrum. Okay, how many of you knows the power spectrum? This is a very useful concept. Now you learn this now. Power spectrum is the Fourier transform of autocorrelation. Okay, power spectrum is the Fourier transform of autocorrelation. Okay, so first, in order to define the autocorrelations, we have to think about the wide sense stationary sequence, ST, for which the following autocorrelation exists, right? Autocorrelation exists. So this is functions of only tau, time difference between the two. So how much these two are correlated, that's actually represented by this, right? So just taking the discrete time Fourier transform, we just multiply to this multiply, exponential minus I omega tau, and then take the summation tau equal minus infinity to infinity, right? We get the discrete time Fourier transform of autocorrelation. That's power spectrum. Okay, so originally we had this autocorrelation and it converted to power spectrum. Well, and the relationship between these two are very interesting. So one particular case is that, well, if autocorrelation turns out to be, signals S is actually totally uncorrelated, we have only one point non-zero, say lambda, all other the zero, right? That is the representation of the uncorrelated signals in the in terms of autocorrelation. If you take the Fourier transform, converting this one to a power spectrum, it turns out that the power spectrum is just a constant throughout this period, then minus pi to pi, just a constant throughout. And then in optics, if you relate this one to wavelengths and then optical frequency, it's just containing all the frequency components equally. That's basically white light. So that's why we call this kind of signals, uncorrelated signals, white signal, white noise. So officially we introduced the white noise at this time. Okay, again, the signal is basically uncorrelated. This is the sound, familiar expression, right? And then we substitute this one into this power spectrum. Let's look at this, okay? So this RE tau takes a non-zero value only when the tau equal actually zero. Tau taking other value, it's just zero. So we don't care this summation, only tau equals zero. So that's lambda, and the times E, tau zero means zeros, right? So that's a lambda. So that's a constant throughout this omega. Of course, this is the special case where totally uncorrelated white signals. If it's a little bit colored, like the example I showed just now. Well, not only this, but also we have some kind of element and component here, right? So if that's a case, it's not actually complete one. It's a band limited white noise. So it's not spanning minus pi to pi, but limited from some band width. So though this one is expressed in a little bit different scale, but basically the same in nature. So bandwidth is not the spanning the whole area, but a minus b to plus b. The corresponding autocorrelation is something like this. It's a unique shape. It's a sinc function. You have heard of that? A sinc function. It shows actually sine functions, sine over x. That's the function like this. Okay. Now with this, what we like to do is a frequency. We basically use the correlation method, convert it to frequency domain, basically power spectrum. And with that, we like to estimate, we like to determine the transfer function, the frequency domain. So transfer function, the frequency domain is basically, we need to do the following things, right? And so just a standard continuous time case, you have a continuous differential equations. You take the Laplace transform, you get the this standard transfer function G of S, right? And then what did you do in order to obtain the frequency the response, frequency transfer function? You replace the S by E I omega, right? Right, E I omega. So oops, sorry, this I omega, I'm sorry, this is the typo, it's a bad typo. S is replaced by I omega, right? That's the things that we did. Yeah, likewise, this is and G of I omega for this, I should not use the same G's over here and here, but I know that that is something that you did, and S is replaced by I omega. Now, likewise, given the discrete time transfer operator, G of Q, and just associated with this, analogous to this story, frequency transfer function can be obtained by replacing Q by, E I omega. So Q is now, replace Q is filled with this E I omega. Okay, so it's same type of a mass. To prove this, it actually needs a few more slides, but I think this is acceptable for you. So in the case of continuous time converted to standard transfer function, S is replaced by I omega. Likewise, in the case of discrete time transfer operator, Q is now replaced by E I omega. Okay, so this is to represent the this one is actually complex functions, and it has the magnitude component and the phase angles, and we can plot the body plot out of it. Now, our objective is to use the cross correlation and autocorrelation, just as we did for time domain, to get rid of to suppress the effect of the noise. We use this technique. So let R U I tau be the cross correlation from input to U to output to Y of a linear time invariant system. Now we take the we convert this one to frequency domain by using the discrete time and the Fourier transform. So that is to define the cross spectrum from input to output. It's basically the power spectrum of the input to output. Excuse me, this is another typo. Yeah, the discrete Fourier transform of input to output to cross correlation. Discrete Fourier transform of the cross correlation RUI. I have two typos here. Maybe I'm sluggish on this page, so sorry about that. I'll clean up all these typo and then post the correct one soon. So just as we obtain the power spectrum by taking the discrete time Fourier transform of autocorrelation, likewise we actually obtain cross spectrum by taking the Fourier transform of the cross correlation. Okay, so this is the definition of phi UI, cross spectrum. Okay, now interestingly, the transfer function G E I omega frequency transfer function can be obtained by taking the quotient between this cross spectrum over power spectrum of the input. Okay, cross spectrum over power input of the input. So let's actually prove this and why this is the case. Okay, so again, it is based on coming from the Wiener-Hopf equation. Okay, you remember the Wiener-Hopf equations? It's basically a relationship between cross correlation to autocorrelation, right? And in between we have this GK sitting, right? So I know just very similar to convolution expression, right? Convolution expression. Okay. Now what we like to do is to look at the Fourier transform of this cross correlation, which is actually a cross spectrum, is given by this definition, right? We take this one here and then multiply an exponential minus I omega tau, and then take the summation minus infinity to infinity with respect to tau. So tau is actually integrated out over here, and it turns out to be the function of omega. Okay. Now let's actually substitute this, cross correlation expression to replace this. So you get this expression, right? Right. So we have two summations. And what you need to do is we swap these two summations, here. But in addition to that, we multiply, exponential minus I omega k and exponential I omega k. So the product of these two is basically 1. So I did nothing wrong. So, but we insert this guy into here to split these two terms in the following way. So first term is actually taking this, exponential minus I omega k and combine this one with this gk and the summation over k. Gk exponential minus I omega k. Okay. And then this one is nothing but the gk's, anyway, let me just keep this guy in here. Okay. The rest of the part is basically I have to take this exponential I omega k, and let's actually combine this guy and then this exponential, result in exponential minus I omega tau minus k, right? This k, the plus, so minus, so plus, okay? And that's actually corresponding to RU tau minus k over here. So if you replace tau minus k by s, this particular part expression becomes RUS, exponential minus I omega s, right? So what is this? So this guy is basically, basically this one is basically a Fourier transform of RU. What is that? RU is actually, input autocorrelation. Autocorrelations Fourier transform is basically power spectrum. So this particular part becomes, phi u omega. Okay, maybe, I just skip a little bit, one step. So here I replace this one by s, but this guy is basically, we have to take the summation tau equal minus infinity to infinity, right? But we do this for every single k specified from this summation. But every single k, we actually, change tau from minus infinity to infinity. That's actually equivalent to saying that s is the value from minus infinity to infinity. So it is, this expression is okay. Replace this and then minus, take this summation over here with respect to s. Okay. Now let's look at this term. I just copy here, right? Copy here. So gk, exponential minus I omega k. Gk is actually, impulse response, right? So, let's recall gq. gq is one, q is actually time shift operator. And we wrote the transfer function or transfer operator by using this expression where impulse response is directly involved, right? And then time shifted in this way, yeah, right? So this is actually polynomials with respect to Q inverse. So if you actually replace this Q by EI omega, this Q replaced by EI omega, this becomes frequency transfer function, GEI omega. If you do so, this Q must be replaced by EI omega. That turns out to be this guy, exponential minus I, omega K, right? K is picked up from here together with the minus. So this terms as a whole is to represent this frequency transfer function, GEI omega. Okay, please actually record the definition of GQ, and the Q is now replaced by EI omega. That's actually exactly this expression. So this turns out to be GI omega. So to make a long story short, this cross spectrum equal the GEI omega frequency transfer function times the power spectrum of the input. So solving this one for GEI omega, it is actually given by the cross spectrum over auto spectrum. Okay, so this is the conclusion. Okay, body plot can be, and then next plot and the same thing can be created by computing cross spectrum over power spectrum. So suppose you are given the time sequence experimental data UT and YT. T go I to many of them. Okay. First thing is actually compute the autocorrelation of the input and the cross correlation with the input. Okay. So first, just correlations to be computed. Okay. Then cross each of them is to be converted to a frequency domain by using the discrete time Fourier transform. The result is basically autocorrelation, power spectrum and cross spectrum. Okay, so that's a point to compute this. But I know this G EI omega is actually a complex function. It has a real part and a negative part. The real part and the imaginary part, and actually a magnitude and the phase. So from here you can plot body plot of magnitude, gain curve, and then phase curve by taking the phase component. Okay. So now it is known that of course, this n longer is better. As n tends to infinity, it is known that this actually, the transfer function obtained in this way, is basically converging to the true transfer function in average. Okay, it's kind of a strange word. If you do this many times, and then actually take the average of that, in average, it is going to converging to the true ones. Oftentimes we put the G naught here to represent this guy is a true value. So true transfer function can be achieved. However, this is in average. In average going there, it doesn't mean that the variance is zero. The variance is still non-zero. So what you get is that if you just run this doing this procedure, you end up with very much in a zigzag and a noisy, the body plot. And you scratch your head, what is this? What the hell? I said everything, Professor Asada said, this is a great method, but I end up with the very zigzag stuff, But that's not the end of the story. Yeah, this is very natural, in particular with the finite n. This is the case. However, it is guaranteed to converge in average. So that said that, if you repeat this experiment a million times, then you, in average, you get the true one. But you don't have to do that because we can assume that this one is somewhat smooth. So even though the one experiment, if you take some clever averaging within some shorter time and frequency window over here, you can get the pretty smooth curve as shown by this solid blue curve in here, smooth curve. So what you need to do is to carefully take some average of the body plot near here. Of course, as you expand this, windows, you get the better average. But that's actually you mix the wrong frequency components here, so that's not good. So we put some kind of weighted average, and this one is a weight function, and there are many actual weight functions that are being used. But one particular one, it's called Hamming windows, is very much famous and very useful. So having the highest weight, at that frequency, and then as you depart from that frequency, the weight is going down a little bit in this way. But we take some average in here, replace that noisy ones by this average value, then you get the very smooth curves like this. So that is basically, the techniques that are being used. So have you played with the kind of spectral analyzers, or most of the oscilloscope? If you buy a little bit high-end oscilloscope, maybe you should ask your advisor to buy the a little bit the better ones, or just the software is actually okay in doing this. What's inside of the spectral analyzer is exactly this guy. So spectral analyzers, samples, input, output, UTYT, right? UTIYT. And then inside it's basically, do this a two-step operation. One is actually computing, autocorrelation and the cross correlations, and then convert it to, power spectrum and the cross spectrum, take the average. And the third step is to apply this, Hamming windows and smooth out this, and then you get to some handsome plot in here. That is the story. Okay. Now, yeah, here are a few more important, basic mathematical properties and about the power spectrum, the cross spectrum, and the frequency, transfer function. The first of all, power spectrum, by definition, this guy is actually even function, even though you replace omega by minus omega, you get the same result, right? So it is actually symmetric with respect to the center point, and omega equals 0, right? And this is just a quick proof. So yeah, this is basically showing, well, in fact this guy is a real function, and all imaginary part gone. Let's look at that. So expanding this and starting with the tau equals 0, RU 0, and exponential zeros, right? And then the tau equal 1, and the tau equal minus 1. Let's put them together. Okay, and the tau equal 2, and the tau equal minus 2. Okay, because autocorrelation is by definition is symmetric, right? RU1 equal RU minus 1, right? Because, definition of RU is basically, UT and the UT plus tau, right? If you swap a UT and the UT plus tau, you get the same results. And so they are symmetric, right? So these two are the same. So I just replace this one this way. Now that, if you look at this, one is actually exponential minus omega tau, omega minus I omega, and the other is plus I omega, right? Remember that the exponential this function is cosine and then I sine, right? And the cosine, even though you have a minus omega, it remains the same, but this one is different. So these two cancel out. The imaginary part is all cancelled out in between these two. And the same thing here, imaginary part is basically sine part, they cancel out. So at the end, you get the all cosine functions, it's all real. So this is the even functions, and they're all real. Cross spectrum is a complex and a skew symmetric function. It's a little bit different. So what it means by this is that then if you swap omega by minus omega, you have to also swap the u and y, this order. So this is actually proof. I think this one is something that's really straightforward, but let's look at that. So I put the minus omega. So here exponential part is not the minus I omega tau, but a plus I omega tau, because the double negative becomes a positive, right? So now I replace tau by minus tau prime. Just to change the sign over here, you get to this expression. But here, that actually, when you actually, swap u and y, u and y, relative time difference actually, swap, right? So RUY tau equal RYU minus tau, right? So if you go back to the definition of, correlation, that's basically expectation of the product between signal u and y, which are different. in time by tau. If you swap u and y, you have to swap this one minus tau, right? So that's the same thing. So this is actually a basic rule. Applying this one, this is now replaced by this yu, uy, I swap, and it remain the same. This is actually, the power, cross spectrum of the input output, basically output to input, the yu that I swap these two. So this is proven. Third, properties which we often see is if in case UT and VT are uncorrelated, but the power spectrum is actually in the power spectrum of the addition of these two and summation of these two is basically individual power spectrum. And the cross part is basically, disappears if these two are uncorrelated. That's actually quite, reasonable, because if you go back to correlation of y, which is actually divided into a u part and a v part, that can be done in this way. Correlation between the two is 0, so that's actually y. And then that remains the same, even though you actually take the Fourier transform. So this is the case. Okay. So now finally, one more actually part, actually two more points which are a little bit tricky. So the squared magnitude of a frequency transfer function is given by this. Okay, so this is somewhat obvious because frequency transfer function is actually a complex function, right? So it takes a complex value like this, a plus ib. So if you basically multiply these two, e I minus I omega, obviously this omega is now replaced by or I is now replaced by minus I, so you get the actually a minus IB, right? So so these two are basically complex conjugate. So if you multiply these two, becomes a squared b squared. So what is this? This guy is basically showing the magnitude of this complex number, right? So in general, it is actually this guy. The magnitude squared is basically this guy is given by the product of these two functions, which are complex conjugate to each other. Okay, and then last one is this. So suppose UT is going through some linear, time invariant systems characterized with the frequency transfer function G of E I omega. Output to YT's power spectrum, phi y omega, power spectrum of this, is given by this expression. First, this actually, squared the magnitude of frequency transfer functions times the power spectrum of the input. So input to power spectrum, going through this, it is actually this output to power spectrum, is given by the input spectrum plus times the squared magnitude of a frequency transfer function. So that is given by this. This is somewhat actually, understandable in result, but the proof is a little long. And I showed some complete proof in the lecture note, chapter 11, page 4 to 5, shows a proof of this guy. Okay, now the reason why I introduce this stuff is to explain the technique. It's called coherence. Coherence is somewhat, this is a widely used technique to evaluate the fidelity of identified transfer function, the G of E I omega. So this if coherence is good, you can actually trust the result that is actually obtained on the transfer function is very likely to be correct. Of course, there are many reasons why you can't get the good transfer functions, and this coherence, evaluation allows you to give you some kind of warning whether things are going, unusual things are going on. You get some kind of a warning from that. The definitions of this coherence is, cross spectrum, magnitude, square the magnitude of cross spectrum over power spectrum of input and the power spectrum of the output. Okay. And then, as I showed you below, this, gamma square is actually to take the value between 0 and 1. And 1 is perfectly high fidelity, and 0 is no fidelity. And it is actually the function of omega. So you can say that in which regions of your frequency omega, you get a high fidelity, and in which region you don't have the good fidelity. So you can get to some kind of kind of quality assurance with respect to your transfer function. So let's look at this model again. So the noise is additive coming to this output. And so you have a linear time invariant system, input to UT, and then observe YT is corrupted with noise VT, but it's additive. So now this part is given by the GT, GQ, and then the input-output relationship can be written in this way. So the power spectrum of output YT can be derived by these two terms, and suppose UT and VT are not correlated, then we can actually split this one into two power spectrum with this part and then this part. This part, the power spectrum, is actually phi v omega. That's actually kind of definition, so we write it this way. And the power spectrum of this part, which is actually noise-free part, the Y bar part of power spectrum, is basically written in this way. Remember that the input to power spectrum going through frequency transfer functions, that is actually output side of a power spectrum. So that is given by this. Okay, we just proved this properties in the previous slide. Now, so if you include this noise, output power spectrum is given by this. So let's substitute this guy into this coherence gamma square. Now, this guy sitting here is basically we have this term over here, right? So this guy we just proved in the previous slide. So we use this guy, right? And then okay. Okay. So phi u y omega. This is actually cross spectrum. Cross spectrum is given by the g e omega the phi u, right? And we have a square of them, so square, and then but the one of them is canceled out with this. So this over phi y. Phi y is now given by this. That's why we got the this expression. So it is obvious that this one and this one the same. So if this phi v omega is 0, then this becomes 1. So that's actually a high fidelity part. So in fact, if you plot coherence, so here's actually a two body plots obtained through the process I explained, and beyond a certain frequency, it is not a little jagged, and even though you're applying the humming, on the windows, but it actually still a little bit, erratic and over here. So you're a little bit, concerned about the fidelity of the estimation, right? So if that's the case, I strongly recommend to compute the coherence. So third plot is a coherence curve. As I said, higher is better. 1 is actually the best, and actually 0 is no confidence. So if you see this, it's a high fidelity up to this point, and after that is declining in some way. So something going on. So one actually obvious, reason is that there's some kind of exogenous disturbance or noise comes into this. Even though, we use the correlation-based method, or even though in the frequency terms, we basically eliminated the uncorrelated noise if the signal is really truly uncorrelated. That's good. However, as long as you have some noise and then uncountable, unidentifiable uncountable noise or disturbance, this actually coherence goes down. And also, some unmodeled effects such as some nonlinearity. There's some nonlinearity. Every system has some nonlinearity to some extent, right? And the question is, to what extent the system has actually a nonlinear effect? And if some part is nonlinear, this coherence goes down. The other reason is that fast Fourier transform. There's actually one more very effective computational algorithms that's called the fast Fourier transform, applied to a discrete time and Fourier transform. And this particular method is somehow effective, but the problem is kind of leak issues. If that problem comes out, then this coherence goes down. So check the coherence. If that's actually a reasonable value, you present your identify the transfer function with confidence. Otherwise, it's to give you some kind of warning, right? So after this point, it's very much useful, but beyond that point, you have to use it with the care, right? Cautious approach is needed. So that's all I need to talk about today. So it's a little actually, intense materials, but absolutely these are useful. And then the industry using this, yeah. So we don't use the simple step response and actually, frequent, sine wave, cosine, the sines. Well, so some situation we use that, but if permitted, we basically supplied some kind of a noise signals, uncorrelated signals, to kill the output, the noise coming into the systems. So you get the more high fidelity identifications. So this is a really quick, non-parametric system identifications. And as far as you deal with some systems, so this is the first step you do before going to a nonlinear representation, before going to some more complex representations. People first try to model this as actually simple linear systems, and this is actually the tools you can use. As far as the goal is just to obtain impulse response. Oops, I think I'm actually passing the deadline. So 4 minutes actually overrun. I shut up my mouse. So this is something useful. So please use it. Okay. Sorry, being overrun. Okay. Take care. Bye.
Thank you.
Thank you.